So it's great to come to Delhi. Please, it's one of the great historic cities. And I hope the conference, along with all the guests, can see essentially a history of India in a microcosm. Okay, so I will start with my talk. And I noticed the theme of the meeting is technology for humanity. So in one sense, my talk about prosthesis is just that. How can we help people with disability? And I'll connect it up with sensors very shortly. Okay, so this is science fiction. So I was a graduate student when this movie came. I hope you know this. Star Wars first movie. What it shows, Luke Skywalker, he lost his arm, father cut it off and with a laser. But now, what is interesting is that the machinery has a sensor built in so that he gets a sense of touch. So that's the kind of focus of my presentation. How can we use sensors to provide a sense of touch or feelings? So let's orient you to prosthesis. This is actually one of my graduate students. He's a bilateral amputee. And today, our technology has moved far enough so he can control this prosthetic hand in a pretty natural sort of way. He's in the lab controlling the hand, the fingers, and so on. This is the mechatronic side of things. What we would like to do is to provide additional capabilities to the prosthesis. Okay, so I'm going to give you a bit of introduction on prosthesis, and then we'll go into topics of sensors and then other broader applications. But if you recall from my title, I also said it's biomimetic. So can we design sensors that are biologically inspired? And I use the word neuromorphic because sensors in our skin connect to our brain via the sensors or receptors in the skin and so on. So let's get inspiration from nature. Okay, so that's the general outline of my presentation. By the way, in his arm, there's a phantom limb, phantom perception. So you see those green and blue dots. Those are, I don't think I can control it. Okay, so those give him a sense of feeling that green and blue colors are perceived at different spots in his arm. So how can we give that sensory information to this young man? That's the question. Okay, so introduction to prosthesis. So history of prosthesis is pretty slow, put it simply. It took about a century from a hook-like device to a dexterous hand that I showed you. By the way, India is also famous for what's called Jaipur foot. So it's very economical or frugal foot or leg for people who have lost the lower limb. So in this case, we are talking about upper limb, and within a century, it kind of moved from hook-like device to now anthropomorphic, human-like hand. And so predominantly, you will see what on the left side, past or in fact, I should say present. This is what you can get to control a prosthetic arm. To the right is the dexterous hand. And in between is a bit of a story. In a way, it's my own journey. So unfortunately, it's tied to all the wars. Early 2000, there was war in Iraq and Middle East, and a lot of soldiers came back with their limbs lost. And that's the tragedy that has spurred actually the incredible research over the last decade or so. So DARPA, Defense Advanced Research Project Agency in the US, funded incredible amount of research in this area. And that led to this really futuristic hands. I say futuristic because they're not entirely available. The one on the top are commercial, they're available. The lower ones are research grade prosthetic hands or dexterous manipulators. And they can now, you can operate individual fingers. So you can control the hand individual finger. It's not actually trivial. I don't have so much time to describe how you can do the control. It's a separate topic, but I'll just give you a very brief introduction. So if you have a prosthetic hand with individual fingers, how do you control it? Well, one option is that you put electrodes or sensors on the arm. Signals from the arm, which are called myoelectric or electromyogram, they can be decoded or deciphered using a pattern recognition algorithm. And from that, you can construct a variety of different patterns so that now I can use that myoelectric signals to decode for movement of an individual finger, or what's really more important, different types of grasps, like pinch or ball grasp, and so on. So that's the acceptable state of the art, and that's what I showed you in the first movie. It's interesting how an entity might actually do it. So this was one of our first subjects. This young woman had lost her arm after cancer, and she had to be operated on. But you can see that there are electrodes, those round circles. Those are the ones that are picking up the muscle signals. And as she thinks about moving a finger, the muscle signals in the forearm change, and then we decode using fairly advanced pattern recognition algorithm, and then she can point to a finger or open and close the hand. So you can, I hope you get some idea of how to control a prosthetic hand. Fast forward, several of my students have spun off a company that actually now makes this kind of prosthetic hand available. And this gentleman, for example, can now use it around the house. He's able to operate the wrist and the hand and the finger and grasp and function in what's called activity of daily living. So I think this is very good. It's affordable in the sense that these things still cost $30,000 to $50,000, so that's not for everyone around the world. I'll talk about it at the very end. But at least something magical, amazing, which is the hand, which is only unique to us humans or perhaps non-human primates, is now under our control. Okay, let's go even a step forward. I mean, if I move my hand, if I control, actually it's my brain, it's my mind that's controlling it. So that's the topic of what's called brain-machine interface, which means we can take signals from the brain. Of course, they carry over to the spine, to the nerves, to the arm. And so this is a very straightforward, simple illustration that actually you can decode even the brain waves, what are known as electroencephalogram, EEG. And on the laptop, you can see some EEG waves. This student of ours is wearing a cap. Those white dots are the electrodes that record EEG signals. And then you can decode those signals to produce control signals for the opening and closing the hand. So that's a very short introduction to brain-machine interface. There is another way to control a prosthetic arm, and that is picking up signals from the nerves. So this gentleman has lost his arm all the way up at the shoulders. So the nerves that carried the signal to the hand or arm now are wired to the chest. So you can see some kind of strange movement on his chest. And that movement is decoded to control the arm. So this is called targeted muscle reinnervation. So you reinnervate the nerves to the muscles and then use muscle signal as an amplifier to decode a movement of the hand. And that's quite remarkable accomplishment by a number of researchers at Johns Hopkins and Chicago and so on. Okay, so that's for the movement, which means our brain controls the machine, right? So signal comes from the brain, through the spinal cord, to the nerves, to the arm. But what about the reverse? Can we carry the sensations back? So that sensory feedback, sense of touch, is the main focus of my presentation today. How can we pick up a sense of touch of when you shake hands, that feeling back to a person? And I think this is after about a decade of work on prosthesis and control, last few years, major focus around the world, or my research is tied to this area. Okay, so part 2 of my presentation is these biomimetic, which means biological skin-like sensors, and neuromorphic sensing, which means how do we encode that information. So when we discuss the idea of sensors in the skin, to electronic engineers, sensors designers, very commonly the word is used e-skin, electronic skin. So I want to create an analogy between the skin and the robotic or prosthetic skin. So first, a little tutorial on the skin. Our skin, the surface, is first few hundred microns has a lot of what are called receptors. These are nature's sensors. Some of them code for touch, some for pressure, some for vibration, and even for pain. These receptors are layered from top to bottom. So you can imagine ones at the top are a bit more sensitive, ones at the bottom code for something else. So that's what we want to mimic in e-skin. So when we apply a pressure, when you touch, when you press on the skin, left side is that finite element model that shows that there is a deformation, and that activates those receptors. On the right side, those color dots show that therefore those receptors, so nerve endings, are going to start activating and producing some sensor signals. So again, this is a graphic of the skin. You can see the sensors are layered. And it's interesting how nature has constructed versus if you go out to buy commercial sensors. If you buy commercial sensors, they are force, pressure sensors, and they produce some analog signal, and you produce digital by analog to digital conversion. Nature does it differently. So it does it by creating these different receptors, and it produces two types of responses, fast and slow. So all of you right now are sitting there not noticing what you're touching until I told you. So that's the slow receptor. They're capturing a bit of pressure, but oh, you raised your hand and you scratched. So that means that's the fast receptor. It's sensitive to change. So what we are doing here is, because our skin, our body has sensors all over the body, which means we cannot be paying attention to everything, except in that slow receptors is capturing and relaying the information to the brain. But the fast receptors are looking at the change. Also, you see that how the signal is produced and relayed. It's in digital form, which is quite remarkable, right? That instead of going through sensor, analog to digital conversion and all of that, and multiplexer and so on, signal is directly produced as spikes. These are action potentials or spikes of the receptors. And you can see fast and slow spikes. So now if we want to create e-skin, then we need to figure out how to encode this information. So we would produce this artificial skin. It would produce these spiking activities in digital form. And then on the back end is some type of neural network. It turns out these are also different layers in our nervous system, but we can design a neuromorphic or biologically inspired network that will encode this information. And so our prosthetic hand would have this e-skin at the tip. It would produce this spike activity, those little black lines that you see, or black dots. Those are individual spike patterns. variety of neural networks, recurrent or other kind of learning neural networks can be used to then convert what I touch into texture or shape. Okay, so now let's go into the journey of sensor design. This is IEEE Sensors Conference. I want to emphasize how you might design sensors that are biomimetic. So tactile sensors, one of the first generation we built is made up of these piezoelectric fabric. So it's multiple layers of conductors and piezo fiber traces. And then by cross layers, we can create a large or high density of sensor arrays, to which we need to develop a scanning system so that we can capture the information from a high dimensional sensor array. So that's our acquisition system. Convert that signals into spikes. So there are well-defined equations available to convert the sensor pressure or pain, other information into spike activity. And then have a neural network. And in this case, it was embedded in a single chip so that it could actually decode the information. So this is the kind of general design of the high density tactile sensor array for E-skin. So when my hand touches an object, texture, shape, what it will produce is what you see in the lower traces, those little dots, spiking activity. And my neural network algorithm then will classify into different categories. So that's what we are doing, right? Soft, rough, or round or square objects. So this is a graphic of the sensor. It's a two-dimensional array. And so if I put my hand on it, it creates a nice two-dimensional pattern of the hand. Again, you can see that it is being encoded in digital format, so which means that those colors represents the applied pressure but spikes the digital activity. Secondly, it encodes for slow and fast information. So slow pressure will be retained, but fast will look for change. And you can adjust the sensitivity of it, which is also, again, we are kind of quite remarkable, right? That you can do a very light touch on your skin and feel it, and you can also tolerate huge amount of pressure. So our skin has huge dynamic range. Commercial, industrial sensors don't do that. So in a nutshell, again, the algorithm. So each sensor will produce spiking activity. And then there is encoding of that using a kernel. Then you calculate different weights in the matrix and then map it to an output. By the way, I want to add one more thing. Like, why, you might ask, why are we going to neuromorphic? Like, why all this spiking and all of that? First of all, it's digital, so that's great. Very good signal to noise ratio, an easy way to relate. But consider this, our body has millions of sensors. If we did this conventionally using conventional acquisition, we would be dealing with huge amount of multiplexing and so on. But digital spiking activity can now be relayed like we do in our nerves in an encoded digital format. It's a technique called address event encoding, which means you can give an address of where the source of the signal is, and it produces spiking activity. So there are a lot of advantages to doing it in a biomimetic way. We get different type of sensors and different type of encoding of the information. In our case, we used an algorithm called ELM, Extreme Learning Machine. It's a very simple single layer neural network. So it takes the information from the sensor and produces output. One reason to do that is so it's very fast, very quick, and can be in very low power design. And it has many advantages. It can be trained very quickly, and it's parallel processing. because we may be dealing with very large number of sensors in E-skin. So while our finger and hand may have large, hundreds of thousands of receptors all over the body, if we want to create a E-skin human suit, you would need some technique like this. And so this is a working design. So in this case, that's a two-dimensional sensor fabric on the left. And if you put an object on it, in the middle you see that data from the sensor is produced as spikes. It's both spatial and temporal. And then the ELM chip on the right side classifies the signal into an object recognition. Of course, this solution is limited to a few different objects and patterns, but it illustrates the principle that you can decode E-skin or electronic skins information into different objects and shapes. Can we get that feeling back? So if I touched, the amputee touched something, how would that person know and feel what he or she touched? So consider on the left side is the prosthetic hand and you're grabbing an object. So of course, our sensor is going to produce the spikes and all that you see on the left side. On the right side, what you see are these spiking activity that can now be relayed as electrical stimulation to different location. So maybe that's one way we can get that feeling back to the amputee. So idea here is to convert the sensor signal into spike activity, that digital spiking activity, and then produce electrical stimulation, which then provides a sensory feedback. And in fact, we can do experiments to do the classification. So lower side graph shows that a subject can actually perceive the force with which they can grab or grasp an object. So if a prosthetic hand is now, let's say, lifting an object and it's heavy versus light, the stimulation feedback can actually tell you whether you're touching a heavy or a light object. Just want to kind of take a detour and give credit to a lot of ongoing research frontier in the sensor area. So today, of course, traditionally, when you think about skin-like sensors, they are resistive, capacitive, piezoelectric. Of course, in industrial situations, magnetic and so on as well. In addition, in parallel, there's a lot of research in MEMS and nano areas. What's relatively new is the use of polymeric and soft materials in sensor design. And that segues into flexible sensors or flexible electronics. So you see a couple of pictures on the right. For example, lower right-hand side shows a soft polymer with sensor or conductors on it and gives you an idea that today there's a lot of interesting activity in the soft electronics or soft sensors. So a few examples. One way we can do this is these fabrics. So these are now textiles that have been woven with either conductors or a variety of piezo sensors, and you can attach them to the skin and provide a sensory perception to the subject. So applications might be to pick up a pulse on the arm using small vibrations or pressure changes on the artery that so for example, in the lower right-hand corner, that sensor might be placed on radial artery and you can pick up a pulse. So that's one example, and this is very industrially relevant. Some other leaders in the field who have pioneered a variety of flexible sensors and electronics. This is an example of work by John Rogers, and he has a huge number of publications, but this shows you that thin and flexible membrane-like sensor arrays can be put on the skin. And in fact, as you make that substrate thinner, it can conform to the skin in a very precise manner. And then depending on sensors you put there, you can pick up information like electrical conductivity or pH or some electrolytes and so on. So this is a very hot emerging area where you design flexible sensors, flexible electronics. In our group, we have used silk as a substrate. It's interesting, we're in India and a lot of people here might also be in China and others. So silk is very common, right? And what can be better for such an application? Silk is biocompatible. It's ultra thin. It can be actually quite strong. Silk can be biodegradable if you implant it, but silk can also be modified to remain as a more robust, reliable, of course, like silk fabric, are used in clothes. So silk has been applied as sensors in various applications. In fact, lower right-hand corner, the picture shows that silk fabric with metal conductor is on the brain surface. So not only skin, but also brain and other tissues. You can apply silk. The work one of my graduate students designed silk-based substrate. It's, by the way, transparent. These are gold conductors, but using indium tin oxide or something, you can make it completely transparent as well. So it's thin, flexible, and transparent. There's some fantastic work by Professor Samaya and his group in Japan. And he has pioneered, again, similar thin sensors and fabrics. So Thakor and I collaborate, but he always uses the prosthetic hand. He himself doesn't work on it. But this is a beautiful graphic that illustrates that flexible electronics and flexible sensors may be very applicable for a human hand. So that's why he got in touch with us so that we can develop these for prosthetics. And they've used a variety of techniques. In this case, E-skin system, which is two-dimensional, made up of, again, variety of substrates, polyimide, and then later on he has been working on sort of nanofiber scales designs. The designs that have now come up make for stretchable substrate as well. So current technology lends itself to not only flexible but stretchable sensors and moving in the direction of stretchable electronics as well. So you can see in this graphic, so these are stretchable wiring and stretchable organic transistors, so organic electronics that is embedded in this substrate. So this is beautiful, right? Now we should be able to make the E-skin made up of our skin stretches. So why not make sensors that are stretchable and electronics that is also stretchable? So these are a few graphics of sensor array on the skin. You can make it wireless by similarly printing the antenna on the substrate and then pick up the signals from it. I mentioned the example of e-textile before. Actually, one of the challenges, the bonding word is that now, unfortunately, the challenge is how do you connect all the electronics and wiring to the sensors that are stretchable and flexible. I think this is a very vibrant area where you have to combine flexible sensors, electronics, connectors, perhaps make it into a self-sufficient, independent device. There's one other pioneer in the field, Fernand Bauer at Stanford, has also similarly worked on organic transistors. And fortunately, nowadays, thanks to work by her and others, these organic transistors are now quite low voltage and low power. In our case, this is a design that was actually popularized to make it look like human skin. Well, so the sensor is pressure sensitive, but it should produce those spikes. Remember NeuroMorphic? So in this case, she used a simple ring oscillator and therefore it produces oscillations that are proportional to the applied pressure. So it's kind of like surrogate spiking signal. And then it's implemented into a closed loop system so that if you see on the left side, a pressure sensor is picking up the signal, that organic electronics produces that oscillations kind of like spikes. So you see that on the right side, those pulses, and then those are transmitted back to a neuron or a brain slice. And more recent, they had a paper in Science about giving it to a cockroach so that it can feel some, stimulus and it could move its antenna in one direction or the other. So it's now a good illustration of a closed loop system of sensing, organic electronics, stimulation affecting the nerve, right? And it's all cutting edge, right? Because we are working with flexible sensors, flexible electronics, organic electronics, and stimulation. Okay, so that was a bit of a detour into cutting edge of sensors and electronics. Let's come back to prosthetics. So I want to say, well, how do I get that feeling back? How does that amputee get the sensor feeling? So the E-skin here is on the hand, or a glove on a prosthetic hand. You see in the graphic on the left side are the fast receptor at work, and on the right side are the slow receptors. So the fast ones are looking at the change, slow ones are looking at the applied continuous pressure. By the way, you see small red dots going out, and those are the nerve signals. So we can now take the sensor input and relay that as nerve information. This is what makes research fun for graduate students. So my graduate students say, oh, okay, a prosthetic hand, if it has to touch an egg, of course it'll break. By the way, you can eat a lot of eggs this way. But with tactile feedback, you can handle very delicate objects as well. So this prosthetic hand with touch sensor is able to handle delicate objects. So we went a step further. Just again, like skin is multi-layer, right? So receptors on the top, receptors below. So we call that e-Dermis. Dermis is for the skin, or epidermis or electronic dermis, which is multi-layer. And so when you put multi-layer sensors, now you can perceive different objects. So object 1 is kind of round, 2 is oval, 3rd is sharp. So what you see in the graphics is upper and lower layer. So upper is red, lower is blue. Different layers for levels of pressure. And at the very bottom, you see the spiking activity. So now, using this sort of multi-layer sensor, I should be able to now perceive the shape of the object from round to very sharp. And it's encoded in this nerve activity that you see in the bottom right. Again, where we are going with it is to improve the perception, the feeling that a prosthetic hand is going to have. So it's possible now by doing this multi-layer sensor, and it's neuromorphic encoding. So equations to the left are how receptors in the skin, we can model them properly with equations. By modifying the parameters, we can also model fast and slow, or called nociceptor. These are pain receptors. So we can even model the painful stimuli. And I'll talk about it in a minute. Okay, so you can see the left object is something I want to touch, but the right object is potentially painful. Okay, so this is the work Luke Osborne, my PhD student, implemented. So this is our prosthetic hand. It has got that e-Dermis or skin at the tip, and it's touching these round, nice objects, all is well. You know, the prosthetic hand is controlled, it's opening and closing. Now it's a sharp object. And what happened? So when you touch something sharp, you react, there's a reflex. So the sensor signal is short-circuited to the spinal cord, and you get that reflex. So this is now modeled. So this sensor is kind of pain receptor, pain sensitive. Again, as you see, that round object, the sensor information is produced. It is relayed to the MPT through electrical stimulation that I talked about earlier. So again, round objects or so on are not responsive, but painful stimulus, there's a reflex. So we built a sensor that is sensitive to touch as well as pain. Okay, so let's now take it to the MPT. In this case, you saw the young man who, in the very first video I showed, is now controlling the prosthetic hand. And, through that control system I showed you, he was controlling the hand. Or actually individual fingers. He is able to pick up these delicate objects. So it's pretty good precision control of his prosthetic hand. And so far, so good. By the way, each time he's getting some feedback, the stimulation feedback, so he feels that he's touching a soft or nice round object, and he is able to handle it. But now we're going to change that object to a sharp object. So when he touches that sharp object, he will get stimulus that is painful. And there is that reflex, because he himself will open up his hand like a reactive, so it drops the object. So I think this is one of the first time we've been able to show that the artificial hand, the prosthetic, has a range of feelings. And they range from simple perceptions of touch to painful stimuli. So I think that was recently published in Science Robotics. It captured a huge amount of interest in kind of press. I think that's because people want to, it's something very human, right? That feeling, like pain. So we get a lot of these reaction from people about how you deal with pain. Some say, I don't want pain, and why are we doing it? On one extreme, another extreme, they realize that that's what makes us human. A prosthetic hand should have a sensory capability to protect itself. That's why we have skin, not just to feel, but to protect ourselves as well. So I think in some way, the sense that amputees can feel, and including feel the pain, is I think, perhaps a big step for us. There's also some ongoing work elsewhere. For example, at EPFL, they are experimenting with implanting this into the nerves of an amputee. So this amputee on the upper right, and you can see on the lower left is a artificial finger, and it's looking at different types of textures. And he gets lower right-hand corner is this nerve stimulation, and then he's able to say, based on the stimulation pattern, whether it's rough or smooth object. Only very small classes, but it's kind of interesting because now signal directly goes to the nerves. So he can predict whether the object is, rough or smooth. Okay, so in the last few minutes, let's talk about current and ongoing or future directions, okay? So I'm trying to convey in this talk that I think we, as humans, what makes us very human is this sense of feelings, right? Feeling of touch, feeling of pain. And I think learning from nature, from receptors in the skin, to how we encode information may help us understand what these feelings are. And to remind you, how we are getting there is by modeling the skin and encoding the skin's receptors as that neuromorphic. So that's why my title, I said biomimetic and neuromorphic, because for different objects, there are these different spiking activity that brain knows how to decode into perceptions of feeling. So maybe that's how we can model the feelings. But really, really do we know? So we need to go to the brain. So we did that actually. We recorded the brain signals. So it shows on the upper right-hand corner is the map of the brain, and the right side in the middle is the part of our brain that is somatosensory cortex. It's the part of the brain that is movement and touch. In the lower right-hand is the video that shows the graphic changes in the brain signals. But this is very beginning. I mean, how does brain sense and feel? This is a ongoing research, but maybe that's how we'll understand what goes on in our brain or goes in our mind. There are many other areas of research. I started to talk about prosthetics, but actually there are a lot more people, particularly in Asia, who get these nerve injuries. This young man, for example, has an intact arm. He's not able to move because his nerves are severe. This happens from traffic accidents, bicycle, motorcycles, you fall, athletics also. And the nerves get damaged, and now you have a limb that doesn't move. If you see a little bit on the table, there's a robotic hand that we can open and close, picking up some of the signals on that. But this person has intact limb, but not motor or sensory control. So what if we gave that? This is a very large number of people. And if we can figure out how to connect to the nerves using this E-skin and all of that, they would have a better life. There is, of course, an industrial world out there. Today, there are many humanoids being developed, and they're mechatronically interesting, and gradually they will have sensory capabilities so that little robotic toy would touch and get smile or feedback. So I can imagine in the future, a lot of commercial activity will be driven by these humanoid or from toy to industrial application. I was in Italy, and there was an exhibit there about skin as a fashion. It doesn't have to be normal skin. It still can be. You can experiment with the skin to make it pretty unusual. It's just an interesting expression of human art. But let's go back to, before I end my presentation, these cutting-edge research and relatively expensive processes, $50,000 prosthetics with all of that is maybe affordable in the US and so on, but not across the world. So there is on the left side, something equivalent of the Jaipur foot. It's very low cost. Of course, it has no e-Dermis or skin, no sensory, it doesn't even control, but it's ultra affordable. On the right side is the advantage of 3D printing revolution. So with 3D printing, you can make simple 3D printed hands that can be controlled. So even that direction where it's low cost, printable, particularly can be useful for children who grow and the hand needs to change with their life. And now equipping it with low cost sensors and low cost actuation might be extremely useful. So this is that choice, right? Perhaps the very end of my presentation. Yes, on the left side, where this is going is, call it cyborg or something like that, this robotic hand, the third hand that can augment our human capability. Sometimes it might be driven by military applications, because that kind of a third hand or robotic hand can carry more load. It doesn't have to, if it's dealing with hot or dangerous objects, your own hand doesn't have to be affected. For example, clearing landmines. So then if you have a landmine, you have to palpate, these kind of sensors might be useful. But on the right side are the very human applications of these young people who are also either through accidents or landmine or all kind of other reasons, even birth injuries, may need very low-cost 3D printed frugal designs. So this is the choice we have to make our sensor technology, our prosthetic technology applicable to both sides of the equation. Okay, so I conclude. as you heard in the introduction, I have two affiliations, so I want to thank my institutions as well as just didn't have the time to give credit to all the students, postdocs, and funding sources who made this work possible. I'll end with a video. It just gives us just before I give the last video, just to remind you, so today I talked about prosthetics, a journey towards better sensors that are both biomimetic and neuromorphic. And I showed a number of advantages of us mimicking nature and perhaps mimicking who or what we do. So I want to end with this sort of remarkable video to just again give us an appreciation of who we are as human beings, what we are capable of. Just a 30 seconds. So isn't that astonishing that what we can do with our hand, there is a movement, touch. We are far from this, right? My prosthetic hand and touch and various things I showed, there's a long way to go. We as human beings are quite remarkable, and I think we have a long way to go, tremendous research to be done. And I want to thank you for your attention. I want to thank Professor Roy, Gyanchandani, Pratap, and Daya, who organized this fantastic conference. I look forward to interacting with you all in the coming days, and I'll take any questions.